Hey everyone, welcome back to the second part of our theory quiz review. In this video, we're going to be covering the trimeriston and TLC experiments. So let's go ahead and let's dive on in. In this lecture or review session, I have about 19 to 20 theory quiz questions. So we're definitely getting the questions in, the info's in. We're really doing our best here to get through all the content for you. So the first thing I want to talk about is just polarity. In this course, we talk about polarity a lot. When it comes down to solvents, you definitely want to have a good indicator of polarity. Like some things you definitely want to know is that water is going to be the most polar for our purposes. Lagroin has no polarity. Also know about hexane. Hexanes has no polarity at all, right? It's pretty low on the polarity pole here. And some other ones that get mentioned pretty frequently are diethyl ether, ethyl acetate, and acetone, right? So those are really the key ones that you want to try to memorize if you can, just because they get talked about the most as of right now, okay? Remember, anything with hydrogen bonds is going to have a high polarity. So methanol, that has an alcohol in it, as does ethanol. So because those guys contain alcohols, we can think of the polarity as pretty decent, right? And then same thing with water. Water also has a high polarity, okay? So the first thing I want to do is talk to you a little bit about the trimeriston experiment and how we started it off. So you'll notice that in this one, I do have a lot of images for you about the experiment. I find it's a lot easier to associate the material when you have an image to think of. Because if I just say, oh, you did solid liquid extraction, you're going to be like, well, what freaking part of the lab was that? I was crying through it. I don't remember what that thing looked like. So the solid liquid extraction, we use a solvent essentially to extract a solute from a solvent. Now, the most common example of a solid liquid extraction that we use every day is coffee beans, right? If you're like myself and an avid coffee drinker, I have about 3 cups a day. What happens is we're extracting caffeine from those coffee beans. So that's a solid liquid extraction, okay? And in this lab specifically, in the trimeriston lab, we used diethyl ether. And with that diethyl ether, our goal was to extract trimeriston from our nutmeg. Okay, so in this lab, we can say that trimeriston is soluble in diethyl ether, okay, at room temp. Now, nutmeg, the majority of it does remain undissolved. However, nutmeg does have some components in it which will also dissolve in that diethyl ether. So it's not just trimeriston that we're dissolving. So ultimately, we're ending up with crude trimeriston. That's what we're going to be working with, okay? So we use diethyl ether to perform that solid liquid extraction, all right? So that means the liquid portion, that's the trimeriston. That's what we're trying to take out. And the solid portion is the remaining nutmeg. Now, this is just an image of trimeriston and what it looks like along with its melting point. I would say it's a good idea to have this melting point value memorized. And one thing I want to mention is that our melting point range is a 1 degree Celsius range. So that is indicative of a pretty pure compound. Okay. All right. Now, once we performed this solid liquid extraction, we went ahead and we moved on to gravity filtration. Now, I just want to talk about the setup a little bit here. For the gravity filtration setup, you had your RBF, you had a stemless funnel, you had a clamp on the neck of the RBF, and then you had your small iron ring supporting your stemless funnel, and you also had your fluted filter paper or your fast flow paper, okay? So that's the setup with nothing in it. And then down here, you'll see that this is the setup once we have some of the reaction occurring, okay? So here we see the watch glass on top. You can see that there's some yellow on that filter paper. So that's all that nutmeg, right? The nutmeg is being trapped in that filter paper, and we're trying to let the trimeriston, along with any soluble impurities, fall through, okay? Now, why do we use a stemless funnel, right? That's always a theory quiz question. Is like, do we use a stemmed funnel or a stemless, and why? So in gravity filtration for the trimeriston experiment, we use a stemless funnel because we want to minimize the amount of contact we're having with the glassware, okay? what you may have noticed is when you were pouring your Erlenmeyer flasks, what you may have noticed is like white precipitate on the outside of that flask. And the reason for that is the ether evaporates quickly. And you're going to end up with some crude trimyristin on the outside of your glass. And that's okay. That happens. But what we want to do is we want to avoid the amount of surface area that we're coming into contact with the funnel. If we had a stemmed funnel, well, then some crude trimyristin could get trapped along the side, right? And that will decrease our yield. We're going to leave some trimyristin behind. So we use the stemless funnel to make sure that we have our yield in order and to minimize the surface area that we're interacting with, okay? Now, at the end of your gravity filtration step, you want to make sure that your RBF is not more than half full, okay? Because our next step would be the rotary evaporator. And it looks like my slides are a little out of order. So what I'm going to do is we're going to go ahead and move on to the rotary evaporator step, and I'll rearrange them before I post them, okay? So we perform gravity filtration. Then we go over and we do rotary evaporation. Now for rotary evaporation, this is going to allow us to remove the liquid, okay? So what you're going to end up seeing is a light yellow powdery substance along the edges when this is finished, and that's your crude trimyristin, okay? Let's talk a little bit about how this machine works. So what this apparatus is going to do is it's going to decrease the inside pressure, causing the boiling point of this compound to also decrease, okay? So we really don't need high heat for this reaction to work, and that's great. You're even going to notice in this lab that your TA probably put some water in the ice bath. And that's because the boiling point of the diethyl ether that's in here is so low that we actually have to cool the water bath a little bit lower than room temp, okay? If your solvent that you're using does have a high boiling point, you can use this water bath. There's an adjustment, and you could make it hotter if you want, okay? Now, what the vacuum does is it accelerates the evaporation process, and it takes the liquid and it draws the vapors away from the liquid, leaving you with that solid. Okay, so it's removing the diethyl ether, and we're being left with just solid crude trimyristin. Okay. One more thing this flask does is you'll notice you touch the guys up here and you actually rotate your flask. The reason we rotate our flask is to prevent the bumping and increase the surface area of the evaporating liquid. Okay, so when you increase the surface area, it's going to dry a lot faster. Okay, and the vacuum, it's going to pull that liquid out much quicker. So we want to rotate to increase the surface area. Okay. All right. Now, what we're going to do next is we're going to do a couple questions on rotary evaporation. Then we're going to jump into the next part of the lab, which was small scale crystallization. And we'll do a few questions on that. Okay. All right. So like the previous video, I want you guys to try this question out, pause this video, and then we'll run through it together. So go ahead. Okay, great. So this first question is stating, explain how the rotation of the round bottom flask in the roto-evaporator speeds up the evaporation process. Well, we just talked about this, right? How do we speed up the evaporation process? Well, the rotation, it increases the surface area of that liquid inside the flask. Right? So by increasing the surface area, it allows us to evaporate much faster of the liquid inside the flask. Inside the RBF. Right? And that's all we're looking for here. Okay? All right. And then I have one more question on this. So this one is a lengthy one. Read it through, try it out, pause, and then we'll run through it together. Alrighty, let's go ahead and do this thing. So during the trimyristin experiment, the rotary evaporator was used to remove diethyl ether from your RBF containing crude trimyristin. Okay. Initially, the water bath was at room temperature. By the time the last student in your section used the rotary evaporator, the water bath of the evaporator was colder. Explain why the temperature of the water bath of the rotary evaporator decreases as the instrument is used over and over. Okay, this is a wordy question. Holy crow, I didn't know this was an English class. So first we got to understand what they're asking, right? So essentially they're saying, you're starting at about room temp in that water bath. By the time the last student gets to it, the water bath is cold. So you want to think about the roto-evaporator system, right? Do y'all remember what we said about the rotary evaporator? The pressure is decreasing, right? So there's some pressure going on when we apply a vacuum. So let's think about that for a moment. If you are applying a vacuum, right, we know the pressure is decreased in the rotary evaporator system. So if we're decreasing pressure, what happens to temperature? Well, if we're decreasing the pressure, we're decreasing the temperature of all of our glassware. So that means the temperature is being decreased for this and this. Now, if your glassware is colder, what does that mean? Well, that means every time we're rotating in this water, right, the water is becoming cooler. So because we have the vacuum being applied, the pressure decreases, causing all the glassware to decrease in temperature. And then your round bottom flask actually cools the water bath a little bit, just a little bit, each time a student uses it. So once you have about 15 students who have used the roto evaporator and you get to that last one, well, this water bath's been cooled enough where it's a bit cooler than when you began. Okay, I hope that makes sense. So let's go ahead and let's put this into words. Okay, so we can say, let me grab my pen here. When the vacuum is applied, vacuum, I always forget how to spell vacuum, is applied, the internal pressure is decreased. The internal pressure throughout the rotary or the roto evaporator is decreased. So then this results in the temperature of the glassware decreasing. So then what happens? That means that every time, sorry about that, guys. I had to step away for just a moment. We're getting our boiler fixed. Anyways, so the results in the temperature of the glassware decreases. So then what happens is your RBF cools the water bath. Cools the water bath. And each student cools it a bit each time it's being used. Cools it a little bit each time. Okay, so that's what's going on with this one. Let's go ahead now and let's move to small scale crystallization. So small scale crystallization was the last step. Remember, for this experiment, there were not any insoluble impurities. So because there are no insoluble impurities, we were able to skip the hot filtration step entirely, right? When we did the benzoic acid lab, we had to perform hot filtration, and that was because we had insoluble impurities. But for this lab, we do not have any insoluble impurities. So we can just go ahead and remove the hot filtration step altogether. All right, so small scale crystallization. The first thing you had to do was you had to dissolve your crude trimyristin in hot acetone and move it to a test tube. You let it cool, and then you put it in an ice water bath. Okay, the rinses with acetone, that's what changes the color from the yellowish color to the white color. It is recommended that 2 wash steps are done in order to achieve a pure compound. Now, let's say this had to dry rather quickly, right? In your case, you had to let this dry overnight. So in order to allow for this to dry overnight when it's completely white, so if we have our test tube, right, and you did all your purification, and now you have just white solvent, solute rather, you have your white crystals. What you want to do is you want to go ahead and you want to spread that out against the walls of the test tube, okay? And what this does is this allows us to increase the surface area. And that's effective in letting it dry overnight rather quickly. Okay, so that way the next morning when you come in to do your melting point, you don't have a wet compound. Okay. All right. So with the small scale crystallization, just a few reminders about the procedure. You wanted to take your pipette bowl and you wanted to squeeze all the air out. Then you wanted to dig it into the bottom of the test tube until it was touching the very bottom. Let go of the pipette bulb, let it fill with air. As your pipette bulb is filling with air, it is also filling with the acetone, okay? Once that bulb is completely filled with air, you then take it out and you discard that liquid into another test tube. And you keep doing that process 2 more times with your acetone rinses, okay? All righty, so let's go ahead and let's do a couple of questions based on small scale crystallization. Now, I really hope you guys like the order of this. I feel like when you associate the questions with the material, the knowledge sticks a bit better. You know, that's kind of how I view it personally. So let's go ahead and let's continue. So go ahead, pause your video, try this out, and then we will run through it together. Alrighty, so in this question, we want to choose all the statements that are true concerning small scale crystallization that you performed during the trimeriston experiment. So we're being told to choose all of the correct choices here, okay? So letter A states to spread the wet product along the sides of the test tube, and that's an effective way to allow the product to dry overnight. Yeah, definitely. When you're increasing the wet, when you're spreading this, when you're spreading the wet product along the sides, you're increasing the surface area. So yeah, that's definitely a great way to let it dry overnight. So A is definitely a valid answer choice here. All right, letter B says, washing the crystallized product with cold acetone removes insoluble impurities. Do you guys remember what we spoke about with insoluble impurities? Insoluble impurities are removed using which method? Hot filtration. So hot filtration removes insoluble impurities. What's actually happening in this wash step is the cold acetone is removing soluble impurities, okay? So B is not going to work. Then C, pipetting solvent out of the test tube performed the same function as vacuum filtration during a large-scale crystallization. That is a correct statement. So when you're using the pipette, you're doing crystallization, right? Just on a smaller scale. So your pipetting is using, or it's serving essentially the same function as vacuum filtration. So C is also correct. D, the proper technique is to place the pipette into the test tube, followed by squeezing the bulb to allow the solvent to be removed. That is incorrect. That is an improper technique. Remember, the proper technique is to first squeeze the bulb, then insert, and then let it fill with air. So D is incorrect. And last but not least, heating the test tube containing the crude sample and acetone in a hot water bath performed the same function as hot filtration during a large-scale crystallization. That's also incorrect, right? We're not performing hot filtration in this experiment. There are no insoluble impurities. So for this question, you should have chosen A as well as C. Both answer choices there get you the full 4 points, and those are the correct answers. Okay? All right, let's try the next one. So go ahead, pause, and then try this one out for yourself. So here we're told, during the trimeriston experiment, Small-scale crystallization was performed using acetone on the crude trimeristin extracted from nutmeg, which we used diethyl ether for. What was the purpose of this crystallization? Okay, so let's read through these answer choices. So what was the purpose of using the acetone and the diethyl ether? So the first answer says to separate and isolate trimeristin from the other compounds of nutmeg that are soluble in acetone. Now we can only choose one answer, so we have to pick the best one. He's okay-ish, I guess. You know, we do use the acetone for that, sure. But it's not the only thing we're using, right? Because with the acetone is not going to solvate the other impurities. So B says to change the extracted trimeristin into a crystalline form that is more soluble in acetone. We definitely don't want to do that, right? We don't want our trimeristin dissolving into the acetone. Okay. C, to convert trimeristin into an isomer that's more soluble in acetone. No. D, to separate and isolate trimeristin from other components of nutmeg that are soluble in diethyl ether. Yes, that is exactly the purpose of the crystallization, right? That's what they're asking for. So they're asking, what's the purpose of the small scale crystallization? Well, we know that when we use diethyl ether, we're extracting trimeristin, but along with trimeristin, there are other soluble impurities that do dissolve in the diethyl ether. So when you are performing your gravity filtration, right, you're developing crude trimeristin, meaning there's trimeristin mixed with other impurities. Okay, so what we want to do, the whole purpose of using the acetone and performing the small scale crystallization is to separate and isolate the trimeristin from the other components of nutmeg that came through when we did the solid liquid extraction with the diethyl ether. Okay. And then looking at E, we want to change the extracted trimeristin into a crystallized form. No. And we don't want to convert trimeristin, right? We're not changing it. We're not converting it. We're just separating it completely, or as best as we can, from the other compounds of nutmeg that also dissolved in a diethyl ether. Okay. All right. So that is everything that I have on small scale crystallization. Now let's go ahead and let's talk about melting point a little bit. So melting point, that's where you go from a solid to liquid. Each compound has a characteristic melting point. It's not super unique because you can have compounds with the same melting point. It basically serves as a guide to identify unknowns. You want to make sure in this course specifically, you identify melting point as a range. Okay, let's keep going. So here I took this from your lecture. This is just what your melting point apparatus looked like. It's good to know the equipment, what each switch does. So the switch on the left was the power. The switch on the right was the vibrator. We don't touch the vibrator and we don't touch the stir. You don't use the vibrator in this lab, and the stir is already set for you, just so that the oil inside keeps moving around. Okay. This was the temperature control dial. This guy had about 5 slots. You use 2 of them, one for your pure trimeristin and then one for your crude trimeristin. Over here, that's like your viewing area where you would turn the light on, and you have a magnifying glass, and that would allow you to look at the samples as they are being heated. Okay, just a reminder that when you are taking a melting point, your first value or your onset temperature, that's the first site of your liquid. And then your second value or your offset temperature, that's the last appearance of solid. So first appearance of liquid, first reading. Last appearance of solid, last reading. Okay. When you are using this machine, there are a few things you want to keep in mind. The capillary tubes themselves, which is this guy here. You don't want to fill it with too much of your pure product. The reason for that is that the heat will not be distributed equally, So the range will appear much wider than it actually is. So even if you do have a pure compound, if you put too much in the capillary tube, you're going to notice the range being wider than you anticipated. Okay. Another thing you want to do is you want to heat pretty slowly. Okay. So this does take about 15-20 minutes to complete. The melting point of trimyristin, hopefully you remember, it's about 56 to 57 degrees Celsius. So when you're heating up your apparatus, heat it until you get to about 40, 35, 40 pretty quickly. Once you reach 35, 40 degrees Celsius, turn that temperature dial down and make sure that you're heating up at about 1 to 2 degrees Celsius per minute. Okay. This will allow you to have the most accurate reading. If you are heating up too fast, what happens is while you're watching here, you notice the first sign of liquid. So you look at the temperature, and then by the time you come back down, the last sign of solid, you missed it, right? So you can't gauge an accurate second temperature reading, okay? So the slower you go in this case, the more accurate your temperature reading will be, because you'll have enough time to look here, look at the thermometer, then check back and check the thermometer again, okay? All right, so how do we rank melting point? Let's talk a little bit about it. So when you're ranking melting point, it's essentially the same as boiling point. So melting point is a characteristic of a pure compound. It indicates how pure your compound is, and it can help you identify it if it's unknown. Now, how do we use melting point to determine purity? Very specifically speaking, the accepted range for a pure compound must be 1 to 2 degrees Celsius, okay? In this course, we always represent melting point as 2 values. So if your melting point is 70 and 70, it's 70 to 70, right? Or 68 to 69, something along those lines. Now, the accepted value must also be plus or minus 5 from the literature value. That doesn't necessarily indicate that your compound is pure. That's just something that you have to make sure is accurate, okay? What's going to tell you whether or not you are pure is that 1 to 2 degrees Celsius range. Okay, that's really what we want to focus on when we are looking for purity in our compounds. Okay, all right. And then we have a little bit about mixed melting point. That can be used to confirm the identity of a compound based on its own melting point. So that's just its own thing. And then here I just have some examples for you. Okay, so here the range is 1 degree Celsius, so that's pure. The range here is 3 degrees Celsius, not pure. And the range here is 4 degrees Celsius, also not pure. Okay. All righty, guys. So far, I hope most of this information is making sense. Up next, we have about 3 or 4 questions related to melting point, and then another 3 or 4 related specifically to the trimyristin experiment. So let's go ahead and let's try those out. All righty, so go ahead, try this question out, and then we will run through it together. All righty, so we are told the accepted literature melting point of benzoic acid is 122 degrees Celsius. Even though it's not part of the crystallization experiment, a Chem 321 student takes the melting point of her crystallized benzoic acid. Her observed melting point is 120 to 121 degrees Celsius. Which of the following statements are conclusions concerning only the purity according to Chem 327 standards of the sample is correct? And they want us to choose all correct choices. So melting point, right? To be a pure sample, we want the range to be between 1 and 2 degrees Celsius. Okay, that's for it to be pure. For it to be an accepted value, you just want it plus or minus 5 of the literature value. Plus or minus 5 does not indicate purity. Okay, now this difference is 1 degree Celsius, so this is a pure sample. So right away, A and B are out. Now we have to decide, is it a pure sample because it's within 5 degrees Celsius of the literature value, or because it's within 2 degrees Celsius of the range? The range is within 2 degrees Celsius. Okay, or is it both? So remember what we said, all we care about is the range. Okay, the reason why C is not a correct choice here is because what if it is within plus or minus 5 of the literature value, but the range itself is 122 to say 125 degrees Celsius, right? That would not be a pure sample because the range is too broad. So when indicating purity, we only want to concern ourselves with the melting point range. Okay, so D was the correct answer here. All right, let's try the next one. Go ahead, pause, and then we'll run through it together. Alrighty, so the melting point of naproxen is known to be 153 degrees Celsius. Which of the following melting point results would indicate a pure sample according to Chem 327 standards? Choose one. So the first thing I would do is say, okay, melting point is 153 degrees Celsius. Using our knowledge, we know that this could be 153 degrees Celsius plus or minus 5. So the total accepted range or the accepted values can be anywhere between 148 and 158 degrees Celsius. Okay, within that 10-degree range, to be a pure sample, the two values we pick must be 1 to 2 degrees Celsius, right? So first, let's take a look. Does anybody fall outside this range? And yes, D does. So D is out. Now let's take a look of the ranges between these guys. To be a pure sample, we need a 1 to 2 degree range. So A has a 1 degree range, B has a 3 degree range, and C has a 3 degree range. So right away, we can see that the ranges for B and C are too wide or too broad. So A is the only melting point that would indicate a pure sample. Okay. All right. Let's keep going. This question, I believe this is a repeat question, but let's roll with it anyways, right? So go ahead, try it out, and then we'll do it together. All right, so the accepted literature melting point of benzoic acid is 122 degrees Celsius. Even though it's not part of the crystallization experiment, a Chem 327 student takes the melting point of her crystallized benzoic acid. The observed melting point is 120 to 121 degrees Celsius. Which of the following statements or conclusions concerning only the purity, according to Chem 327 standards, of the sample is correct? Once again, when we are talking about purity, we're focused on the melting point range. Okay, so 120 to 121, that has a range of 1 degree Celsius. So this is a pure sample. Okay, then from there, we can see that it's a pure sample because of B. The observed melting point range is within 2 degrees Celsius. Okay, so that's what gives it away here. All right. Now, those are all the questions I have on melting point. Now we're going to jump into questions about the trimerstin experiment itself. Okay. So go ahead, pause, and try this one out. All right. So select the statement that is true concerning the trimerstin experiment. Letter A, diethyl ether is used to dissolve nutmeg. Is that true? That is not true. Right? Diethyl ether was used to dissolve trimerstin, as well as the other solutes that were contained in nutmeg that were relatively nonpolar. Okay, that's what diethyl ether was used for. So this is an incorrect statement. Okay, letter B. A cork was used during the solid liquid extraction phase to prevent the solution from bumping. If you remember solid liquid extraction, remember photos to associate with your memory. This was the cork we used in solid liquid extraction. There was no bumping going on here. That cork, what was its purpose? What do you think its purpose was? It was to prevent evaporation of the diethyl ether. So B is wrong. C, a stemless funnel was used as opposed to a stemmed funnel during the filtration step because the stem of the stemmed funnel is too long to fit into the RBF. Now, part of this statement is true. The stemless funnel was used instead of the stemmed funnel. The reasoning, however, was to minimize the surface area. Okay, we didn't want to lose our crude trimerstin product, so C is incorrect. And last but not least, trimyristin has pure solubility in diethyl ether. That is also incorrect, right? That is not a true statement because the whole purpose of using the diethyl ether is to dissolve the trimyristin, right? That's why we're using the solid liquid extraction. So D is also incorrect. So this is one of those cases where none of the statements above are true, okay? All right, let's go ahead and let's try 13. So try this guy out and then we will run through it together. All right, in the trimyristin experiment, diethyl ether is used in part A to perform the solid liquid extraction. Correct. Acetone is used in part B to perform a small scale crystallization. Also correct. A student mixes up the instructions and performs a solid liquid extraction of nutmeg in part A using acetone. What's the expected consequence of using acetone in part A and why? Okay, so let's think about what these solvents do first off, right? It's kind of how you have to think about these questions, especially when they get wordy. So diethyl ether, we use that to extract trimyristin from nutmeg, right? That was a solid liquid extraction. So the liquid in that Erlenmeyer flask, that was trimyristin along with other soluble impurities, okay, that are in nutmeg. So if we don't use diethyl ether and we use acetone instead, let's think about what might happen. Well, trimyristin, it's not a very polar structure, right? If you think back to what trimyristin looks like, it looks like this guy. So there's no hydrogen bonding. The polarity of trimyristin is relatively low. If you also use this guy that I gave you, the different polarities, you'll see that diethyl ether is pretty low in polarity and acetone is much more polar. So we want to think about how that's going to affect our results. So what is the likelihood that trimyristin will separate for nutmeg if we used acetone? Very slim, right? Because acetone's polarity is huge. Now, when we use acetone, right, in the small scale crystallization, it doesn't really remove the trimyristin, right? Don't we use acetone to remove the other impurities in nutmeg? Right? That's the purpose of the acetone. So what we can say here is either none or very little. Okay, so either none or very little trimyristin. Will come out or be extracted. Will be extracted. Will be extracted from nutmeg. And then this is because the acetone is used for the crystallization. Right? So what does that play into then? If acetone is used for the crystallization, that means the trimyristin is poorly soluble in acetone at room temp. Okay, so this is because acetone is used for crystallization. So trimyristin is poorly soluble in acetone at room temp. Okay, you can also mention the polarities of the solvents, things like that, but this is basically the gist of it. Okay, so by using the polarity, it kind of got me to this end result or this conclusion. Okay, all right, let's go ahead and try the next one. Pause, try it out, then we'll run through it together. All right. So a student performing the trimyristin experiment has crystallized her product using small-scaled crystallization in acetone. Beautiful. That's what we're supposed to do. She goes to wash her product, but accidentally uses cold diethyl ether instead of cold acetone. That's enough to make anyone cry. Her entire product in the test tube dissolves in the cold ether. What should the student do to fix this? Okay, I'll tell you what I'll do. I'll cry, go to my TA and be like, tell me what to do. Okay, I fudged up my experiment. I can't fail this class. So let's talk about these steps, okay? So she's doing small scale crystallization. And when she goes to wash, she uses cold diethyl ether instead of acetone. Well, let's talk about what's going on, okay? When we're at the small scale crystallization step, in our test tube, we have crude trimyristin, right? And we want to purify it. So what happens when you mix crude trimyristin with diethyl ether? It dissolves, right? They tell us it dissolves, but I just want you to think back. Okay, so in the beginning of the lab, right, our very first step was to mix diethyl ether with the nutmeg. How do you get rid of the diethyl ether? Will this student need to start over? And the answer to that is no. There is a way to remove the diethyl ether. Do you remember the technique we used or the equipment we used to remove the diethyl ether? If you said rotary evaporation, you are totally correct. The whole point of the rotary evaporation was to evaporate the diethyl ether off from the crude trimyristin. So that's all we have to do here. We just have to roto-evaporate again. So we want to roto-evaporate, and then they'll perform the small-scale crystallization. So now that we've come up with that idea, let's see if there's any answer choices that match this. Okay, and they're telling us just to choose one. So A, add cold acetone. No, that's bad. B, put the test tube in a hot water bath until the ether evaporates to allow crystallization. I don't like that. Plunge the test tube into an ice water bath until enough product crystallizes and then pipette out the solution. It's not going to crystallize, right? This diethyl ether, it's dissolved. We got to get rid of the diethyl ether. Transfer the solution to a round bottom flask. Rotary evaporate off the solvent and perform small scale crystallization again. Yes, that is perfect. Okay, D is the answer we want to go with. E, student will need to start the entire lab experiment. No, avoid that. You want to avoid restarting the lab experiment. Okay, there's not enough time. So hopefully everybody understands why we chose D. All right, pause, try this guy out and see what you come up with. Alrighty, so explain how the rotation of the round bottom flask in a roto evaporator speeds up the evaporation process. So what happens when we rotate? Well, when we rotate, we increase the surface area, right, of the liquid inside the RBF. And that's all you have to write for this. Just you increase the surface area of the liquid inside the RBF. That's why we're going faster, right? That's how we speed up the evaporation process, by increasing that surface area. You'll notice that a lot of the processes and a lot of the things we do, they can be solved by increasing the surface area, right? Question for you that's not on these questions. What's another thing that we did that involved increasing the surface area? What was something else that helped when you increase the surface area? Anybody remember? It's the drying step, right? During the drying step, when you're done with small scale crystallization, if you take the pure trimyristin that you have extracted, right, increase the surface area along the test tube, and it'll dry faster overnight. Okay, so increasing the surface area could help in a lot of different ways. Just keep that in the back of your minds. Alrighty, now I believe this is the very last question I have for trimyristin. So pause, try it out, and then let's run through it together, okay? All right, during the trimyristin experiment, diethyl ether was the solvent used for the solid liquid extraction step. Acetone was the solvent used for small scale crystallization. Yes. At the end of the experiment, some of your glassware contained small amounts of trimyristin on the sides of the flask. Describe the best way to clean that glassware at the end of the lab. Okay, we talked about this, didn't we, a little bit? Where you have your Erlenmeyer flask and there's like some white stuff on the outside. right? Because the diethyl ether evaporates so quickly that you get some product on the outside of your flask. So we talked about that a little bit. So we need to clean our glassware that has trimyristin on the sides. So ultimately, we need to remove the trimyristin, right? So when I think about removing, I think about dissolving. Who's going to dissolve the trimyristin? Diethyl ether or acetone? What do y'all think? Excellent. If you said diethyl ether, you are correct. So your first step is to rinse with diethyl ether, right? That will dissolve the trimyristin. Okay. Once you rinse with diethyl ether, what do? You empty it into liquid waste. Now, is it done? No, right? It's still contaminated. If we have to use it next lab, there's going to be trace amounts of diethyl ether. So now, after that, you want to rinse it with acetone. Right? So it's really just the first step. We rinse with acetone because, as you've noticed in all the labs we performed, anytime that we are rinsing glassware at the end, we use the acetone that's right there in those squeezy bottles. Rinse with acetone, dump it, and then we'd rinse a little bit with water, dump it, and then clean it. So here we rinse with acetone, you dump that into liquid waste. Then you rinse it with water. That also goes into liquid waste because there's trace amounts of acetone in there, and we do not want any of that acetone to go down the sink drain. Okay, empty into liquid waste. And then finally, step 7, you can clean it with soap and water. Okay, on your theory quiz, make this more of a paragraph. I just listed the steps so it was easier to see. But once again, the reason we rinse with diethyl ether first instead of acetone is because diethyl ether is the solvent we used in this experiment to dissolve the trimyristin. So if we want to remove the trimyristin from the side of the flask, diethyl ether is the best approach because it will allow it to be dissolved and easier to clean. Okay. Alrighty, everybody.